Look up at the night sky and imagine seeing it as our ancestors did. Points of light scattered across the darkness, mysterious, unreachable, divine. For most of human history, the heavens remained distant and unknowable, their secrets locked beyond the limits of the human eye. But then, at the turning point between the medieval and modern worlds, something extraordinary happened. Humanity created a tool that would change everything, that would extend our vision across unimaginable distances and fundamentally transform our understanding of our place in the cosmos. The story of the telescope begins not with grand astronomical ambitions, but with something far more humble, the work of spectacle makers in the Netherlands around the year 1608. These craftsmen had been grinding lenses for eyeglasses for centuries, understanding through practice and intuition how curved glass could bend light, could correct the failing vision of aging eyes. But someone, and history cannot quite agree on who, made a curious discovery. If you took two lenses and arranged them just so, holding them at arm's length and peering through both at once, distant objects suddenly appeared closer, clearer, magnified in a way that seemed almost magical. Three men would claim this invention almost simultaneously: Hans Lippershey, Zacharias Janssen, and Jacob Miesjes, all working in the Netherlands within months of each other. Lippershey, a spectacle maker in Middelburg, applied for a patent in October 1608 for a device he called a kijker, a looker. The story, perhaps apocryphal but delightful nonetheless, suggests that the discovery might have been accidental, noticed when someone in a lens workshop happened to look through two lenses aligned by chance and saw a distant church weather vane appear suddenly, startlingly near. The Dutch government recognized the military potential immediately. Imagine being able to see enemy ships while they were still far out at sea, to count their guns before they came within firing range, to observe troop movements from a safe distance. They tried to keep the invention secret, to maintain a strategic advantage. But this was the age of printing presses and postal networks, of merchant ships carrying not just goods but information across Europe. Word of the Dutch spyglass spread rapidly, and within a year, similar devices were being constructed in France, England, and Italy. The early telescopes were crude instruments by later standards, magnifying objects only 3 or 4 times, producing images that were blurry around the edges, distorted by the imperfect glass and simple design. They were toys, really, curiosities for the wealthy, instruments for sailors and soldiers. No one yet imagined pointing them at the stars. The heavens were the realm of philosophy and theology, understood through ancient texts, primarily Aristotle and Ptolemy, that described a perfect, unchanging celestial sphere with Earth at its center. Why would you need a telescope to observe what was already known, already understood? But in Padua, Italy, a mathematician and natural philosopher named Galileo Galilei heard about the Dutch invention in the summer of 1609. Galileo was then in his mid-40s, already known for his work on motion and mechanics but not yet famous, not yet the figure who would challenge the foundations of cosmic understanding. When news of the spyglass reached him, he immediately grasped its potential, not for military purposes, though he would eventually present one to the Venetian Senate with exactly that application in mind, but for something far more profound. Galileo had never seen one of the Dutch devices, but he understood optics, understood lenses. Working from descriptions alone, he constructed his own telescope in the late summer of 1609. His first attempts magnified objects about 3 times, similar to the Dutch versions. But Galileo was not satisfied with mere replication. He improved his grinding techniques, experimented with different lens combinations, refined his designs. By November 1609, he had built a telescope that could magnify 20 times, far superior to anything yet created. And then, on a clear night, He did something that would change human history. He pointed his telescope at the moon. What he saw astonished him. The moon, which philosophers had insisted was a perfect sphere, smooth and unblemished as befitted a celestial body, was nothing of the sort. Through his telescope, Galileo saw mountains and valleys, craters and rough terrain, a landscape not unlike Earth's. He measured the heights of lunar mountains by observing their shadows, calculating peaks that rose 4 miles above the moon's surface. The heavens were not perfect and unchanging. They were physical, material, comprehensible through the same mathematics that described falling stones and rolling balls. Over the following months, Galileo turned his telescope to other celestial objects, and each observation brought new revelations that shattered ancient certainties. In January 1610, he observed Jupiter and noticed 3 small points of light near the planet. He initially thought they were stars. But night after night, he watched these points move, changing position relative to Jupiter. Sometimes there were 3 visible, sometimes 4. He realized with mounting excitement what he was seeing. These were moons orbiting Jupiter, just as our moon orbits Earth. This was revolutionary, direct observational evidence that not everything in the heavens revolved around Earth. Galileo published his findings in March 1610 in a small book titled Sidereus Nuncis, The Starry Messenger. Written in Latin so scholars across Europe could read it, the book described his telescopic observations with careful precision. He dedicated it to Cosimo de' Medici, the Grand Duke of Tuscany, and named Jupiter's moons the Medicean stars in honor of the Medici family. A savvy political move that secured Galileo a position as court mathematician in Florence. But more than securing patronage, the starry messenger announced to the world that the cosmos was stranger, more complex, and more wonderful than anyone had imagined, and that a simple tube with 2 pieces of glass could reveal these cosmic secrets to anyone willing to look. The publication of the Starry Messenger created a sensation across Europe. Here was tangible, observable evidence that contradicted centuries of accepted wisdom. Scholars rushed to obtain telescopes of their own, to verify Galileo's claims or to challenge them. Some were skeptical. Could these observations be trusted, or were they merely illusions created by the lenses, tricks of light and glass? Others were troubled by the theological implications. If the heavens were not perfect, if Earth was not the center of all motion, what did this mean for humanity's special place in God's creation? Galileo continued his observations with methodical determination. He turned his telescope to Saturn and saw something strange. The planet appeared to have ears or bulges on either side. His telescope was not powerful enough to resolve what he was actually seeing, Saturn's magnificent rings, but he knew he had discovered something unprecedented. He observed Venus and noticed something crucial. The planet showed phases like the moon, growing from a crescent to nearly full and back again. This observation provided powerful evidence for the Copernican model of the solar system, which placed the Sun, not Earth, at the center. If Venus orbited the Sun, it would show phases. If it orbited Earth, it would not. The Copernican theory, that Earth and the other planets orbited the Sun, had been proposed decades earlier by Polish astronomer Nicolaus Copernicus in his 1543 book, De Revolutionibus Orbium Celestium. But it had remained largely a mathematical hypothesis, a computational tool that some astronomers found useful but few truly believed reflected physical reality. Galileo's telescopic observations changed everything. Here was empirical evidence, visible to anyone with a telescope, that the Copernican model better explained what we actually saw in the heavens. But this truth came at a cost. In 1616, the Catholic Church declared that the idea of a sun-centered solar system was foolish and absurd in philosophy and formally heretical. Galileo was warned not to teach or defend Copernican theory as physical fact. For a time, he remained cautious, but by 1632, he published Dialogue Concerning the Two Chief World Systems, a book that compared the Ptolemaic Earth-centered model with the Copernican Sun-centered model. Though written as a dialogue and ostensibly neutral, the book clearly favored Copernicus. The result was inevitable. Galileo was summoned to Rome, tried by the Inquisition, found guilty of heresy, and forced to recant his views. He spent his final years under house arrest, forbidden to publish on astronomical matters. Yet even as Galileo faced persecution, the telescope continued to evolve and spread. Across Europe, natural philosophers and astronomers were building their own instruments, each trying to see farther, more clearly. One fundamental problem plagued these early telescopes: chromatic aberration. Because different wavelengths of light bend by different amounts when passing through a lens, images appeared surrounded by colored halos, blues and reds bleeding at the edges, making observations frustratingly imprecise. The only solution anyone knew was to make telescopes with very long focal lengths, which meant making them extraordinarily long. By the mid-1600s, astronomers were constructing what became known as aerial telescopes, instruments so long they were nearly unwieldy. Johannes Hevelius in Gdansk built telescopes up to 150 feet long, requiring elaborate scaffolding and multiple assistants to operate. These ungainly instruments were difficult to point accurately and swayed in the slightest breeze, but they reduced chromatic aberration and provided clearer images than shorter telescopes could achieve. Observing through them required patience and persistence, but the rewards were extraordinary. Christian Huygens, a Dutch mathematician and astronomer, built aerial telescopes of his own, including one that stretched 123 feet, and in 1655, using a telescope of about 12 feet, he made a discovery that had eluded Galileo. Observing Saturn, Huygens saw what Galileo's ears actually were: a thin, flat ring surrounding the planet, inclined to our line of sight. It was a revelation that captured the imagination of scholars across Europe. Saturn, already the most distant planet known, possessed this elegant, impossible-seeming feature, a ring hanging in the void. Huygens also discovered Titan, Saturn's largest moon, demonstrating that Jupiter was not unique in having satellites. Around the same time, another innovation was quietly transforming telescopic astronomy: the micrometer. Invented in the 1630s and refined over subsequent decades, the micrometer allowed astronomers to make precise measurements of angles in the telescope's field of view. This meant they could accurately determine the positions of stars and planets, measure the diameters of celestial bodies, track the motions of Jupiter's moons with unprecedented precision. Astronomy was becoming quantitative in new ways, moving beyond mere observation to exact measurement. As telescopes improved and observations accumulated, a new picture of the solar system emerged. In 1659, Huygens determined the rotation period of Mars by watching surface features move across the planet's disk. Giovanni Cassini, working at the Paris Observatory in the 1670s and 1680s, discovered 4 more moons of Saturn and observed the gap in Saturn's rings that would bear his name, the Cassini division. He also made detailed observations of Jupiter's Great Red Spot, that enormous storm that has raged for centuries. Each discovery revealed the planets not as points of light or philosophical abstractions, but as worlds, complex, dynamic, worthy of study in their own right. The telescope was also revealing the stars themselves in new ways. Through even modest telescopes, single stars sometimes resolved into pairs, binary systems where 2 stars orbited each other. The Milky Way, that cloudy band across the night sky, revealed itself through the telescope to be composed of countless individual stars, packed so densely that the naked eye blurred them together. The universe was suddenly more vast, more populated than anyone had imagined. If each star was perhaps a sun like ours, might they too have planets? Might we be just one world among countless others? Yet for all these discoveries, the refracting telescope, using lenses to gather and focus light, remained fundamentally limited. The chromatic aberration problem persisted, forcing astronomers to build ever longer, more unwieldy instruments. Some observers experimented with water-filled lenses or combinations of different types of glass to reduce the color distortion, but no solution proved truly satisfactory. The quality of glass itself was another limitation. Bubbles, impurities, and imperfect polishing degraded images. And there was a practical limit to how large a lens could be made. Glass is heavy, and large lenses sag under their own weight, distorting the very images they're meant to focus. The solution to these problems would come from an unexpected direction, from a different type of telescope altogether, one that used mirrors instead of lenses, one that would be perfected by a young Cambridge scholar who would revolutionize not just astronomy, but all of physics. In 1668, a young Isaac Newton, then just 25 years old and a fellow at Cambridge University, presented the Royal Society of London with a curious instrument. It was small, barely 6 inches long, yet it could match the performance of refracting telescopes many times its size. Instead of using lenses to gather and focus light, Newton's telescope used a curved mirror. Light entered the open tube, struck a concave primary mirror at the bottom, and reflected back to a small flat secondary mirror angled at 45 degrees, which directed the light out through an opening in the side of the tube to an eyepiece. It was elegant, compact, and it solved the chromatic aberration problem entirely. Mirrors reflect all wavelengths of light equally, producing no color distortion. Newton wasn't actually the first to conceive of a reflecting telescope. That honor belonged to Scottish mathematician James Gregory, who had published a design in 1663. Though he was never able to build a working version, the mirror-making technology of his time simply wasn't adequate. Italian priest and scientist Niccolò Zucchi had also experimented with mirrors decades earlier. But Newton succeeded where others had failed, grinding and polishing his own mirrors from a special metal alloy called speculum metal, a mixture of copper and tin that could be polished to high reflectivity. His telescope worked, demonstrating that reflection could be a practical alternative to refraction. Yet, despite Newton's success, reflecting telescopes did not immediately replace refractors. The speculum metal mirrors tarnished quickly, requiring constant repolishing. They were also difficult to cast without bubbles or flaws. And there was a certain conservatism among astronomers. The refractor was familiar, its problems understood, while reflectors seemed experimental, uncertain. For several decades, both types coexisted, each with passionate advocates, each slowly improving through incremental innovations. The breakthrough that would eventually make refractors competitive came in 1733, when English amateur optician Chester Moore Hall discovered that by combining 2 lenses made from different types of glass, crown glass and flint glass, he could largely eliminate chromatic aberration. Each type of glass bent different wavelengths of light by slightly different amounts, and by carefully choosing their shapes and spacing, these differences could be made to cancel out. Hall kept his discovery largely private, but the principle was independently rediscovered and publicized in 1758 by London optician John Dolland, who received a patent for what became known as the achromatic lens. The achromatic refractor transformed observational astronomy. Suddenly, telescopes could be shorter, more manageable, yet provide crisp, color-free images. Observatories across Europe began commissioning achromatic telescopes, abandoning their unwieldy aerial instruments. The improved optics revealed fainter stars, finer planetary details, subtler features than had been visible before. Astronomy was entering a new era of precision, where patient observation could reveal patterns and changes that occurred over years or even decades. William Herschel, a German-born musician who had emigrated to England and taken up astronomy as an obsession, became the greatest telescope maker of the late 18th century. Herschel was not satisfied with merely purchasing instruments. He ground his own mirrors, hundreds of them, constantly refining his technique, seeking ever greater light-gathering power. His mirrors were works of art, polished to extraordinary smoothness. In 1781, using a telescope of his own making with a 7-inch mirror, Herschel made a discovery that stunned the astronomical world. A new planet, the first discovered since antiquity. The object, which would eventually be named Uranus, appeared as a tiny greenish disk rather than a point of light, revealing itself as a planet through its apparent size and motion against the background stars. The discovery of Uranus expanded the known solar system dramatically. Suddenly, the boundary of our cosmic neighborhood had doubled. Uranus orbited twice as far from the Sun as Saturn. Herschel became famous overnight, was appointed King's Astronomer by George III, and received funding to build ever larger telescopes. His greatest achievement was a reflecting telescope with a 48-inch mirror and a 40-foot focal length, completed in 1789. This enormous instrument, the largest telescope in the world for the next 50 years, required elaborate scaffolding and assistance to operate. With it, Herschel catalogued thousands of new nebulae and star clusters, mapped the structure of the Milky Way, and discovered 2 moons of Uranus and 2 of Saturn. Herschel's work revealed that the universe was far more complex than anyone had imagined. Those fuzzy patches visible in telescopes, nebulae, were not all the same. Some resolved into clusters of individual stars when viewed through powerful telescopes. Others remained cloudy and indistinct no matter how much magnification was applied. Were these latter objects clouds of glowing gas? Were they perhaps other galaxies, entire systems of stars so distant they appeared as mere smudges? Herschel suspected the latter, proposing what he called island universes, separate stellar systems scattered through infinite space. The idea was almost too vast to comprehend, and it would remain controversial for more than a century. As the 19th century began, telescope technology was advancing on multiple fronts. The achromatic refractor reached new levels of sophistication. In 1824, German optician Joseph von Fraunhofer built a refractor with a 9.6-inch objective lens for the Dorpat Observatory in Estonia, at the time, the largest and finest achromatic telescope in the world. Fraunhofer was not just a telescope maker but a pioneer in understanding light itself. He invented the spectroscope, an instrument that spread starlight into its component colors, revealing dark lines at specific wavelengths. These Fraunhofer lines, as they came to be known, would eventually unlock the chemical composition of the stars, but that realization lay decades in the future. Reflecting telescopes, meanwhile, were benefiting from improvements in mirror technology. In 1856, German chemist Justus von Liebig developed a process for depositing a thin layer of silver onto glass, creating mirrors that were far superior to speculum metal, more reflective, more durable, easier to resurface when they tarnished. Silver-on-glass mirrors revolutionized reflecting telescopes, making them practical for regular use. By the mid-19th century, both reflectors and refractors were achieving remarkable performance, each suited to different types of observations. The greatest refractor of the 19th century was built for the Lick Observatory in California, completed in 1888. Its objective lens measured 36 inches in diameter, a stunning achievement in glass-making and optical design. The 2 glass discs that formed the achromatic doublet had to be perfectly shaped, perfectly polished, and perfectly matched to eliminate chromatic and spherical aberration. The telescope's tube stretched nearly 60 feet, housed in a dome that became an iconic symbol of astronomical ambition. With this instrument, astronomers discovered the fifth moon of Jupiter, resolved previously unseen details in planetary atmospheres, and catalogued thousands of double stars with unprecedented precision. Yet even as the great refractors reached their zenith, the future belonged to reflectors. Glass lenses had a fundamental limitation. Light had to pass through them, and glass absorbs some wavelengths, particularly in the ultraviolet and infrared. Large lenses were also extraordinarily heavy and could only be supported at their edges, causing them to sag slightly and distort the image. Mirrors, by contrast, could be supported from behind across their entire surface. They could be made much larger without the structural problems that plagued lenses. And they reflected all wavelengths equally, opening windows into parts of the spectrum that lenses rendered invisible. The turn of the 20th century brought a new era in telescope construction, driven by American ambition and industrial wealth. In 1897, work began on what would become the largest telescope in the world, a reflecting telescope with a 60-inch mirror for the Mount Wilson Observatory in California. The project was funded by Andrew Carnegie, the steel magnate turned philanthropist, who believed that advancing scientific knowledge was among the highest uses of wealth. But even with unlimited funding, creating such an instrument pushed the limits of what was technologically possible. The 60-inch telescope saw first light in 1908 and almost immediately began producing revolutionary discoveries. But its creators were already planning something more ambitious. George Ellery Hale, the visionary astronomer who had founded Mount Wilson, convinced businessman John D. Hooker to fund an even larger instrument, a telescope with a 100-inch mirror, nearly twice the light-gathering power of the 60-inch. The mirror blank, cast by the Saint-Gobain Glassworks in France, arrived in Pasadena in 1908 and took nearly a decade to grind, polish, and figure to the required precision. The Hooker telescope finally began operations in 1917, and for the next 30 years, it would be the most powerful eye on the universe humanity possessed. With the 100-inch Hooker telescope, Edwin Hubble made one of the most profound discoveries in the history of science. In 1923 and 1924, he observed the Andromeda Nebula and resolved individual stars within it, including Cepheid variables, stars whose brightness oscillates with a known period related to their intrinsic luminosity. By measuring how faint these Cepheids appeared, Hubble could calculate their distance, and the answer was staggering. Andromeda lay nearly 1 million light-years away, far beyond the boundaries of our own Milky Way galaxy. This was proof that Herschel's island universes were real. Andromeda was an entire galaxy, comparable in size to our own, and the universe was vastly larger than anyone had imagined. Hubble's discoveries didn't stop there. By 1929, after observing dozens of galaxies and measuring their distances and velocities, he noticed something extraordinary. The farther away a galaxy was, the faster it appeared to be moving away from us. This relationship, now known as Hubble's law, suggested that the universe itself was expanding, that space was stretching, carrying galaxies apart. It was direct observational evidence for what would become the Big Bang Theory, the idea that the universe had a beginning, that it emerged from an incredibly hot, dense state billions of years ago and has been expanding ever since. A telescope, this instrument born from spectacle makers' experiments, had revealed the origin and fate of everything that exists. Throughout the first half of the 20th century, telescope technology continued to advance, but progress was incremental rather than revolutionary. The challenge was always the mirror, making it large enough to gather more light, yet smooth enough to produce sharp images. Glass mirrors had to be thick to avoid sagging under their own weight, but thick glass took weeks or months to cool after casting, and even then would flex and distort with temperature changes during the night. In 1934, the Corning Glass Works developed Pyrex, a borosilicate glass with very low thermal expansion that solved much of the temperature problem. But the challenge of size remained. The next great leap came in 1948 with the completion of the 200-inch Hale telescope at Palomar Observatory, also in California. The project had been conceived in the 1920s, again with funding from the Rockefeller Foundation, but the technical challenges were immense. The Pyrex mirror blank weighed 20 tons and took 11 years to grind and polish. The telescope's mounting had to be massive enough to support this weight yet precise enough to track stars smoothly as the Earth rotated. When it finally began operations, the Hale telescope doubled the reach of the hooker. It could see objects 4 times fainter, reaching twice as far into space and thus twice as far back in time. With the Hale telescope, astronomers began to probe the edge of the observable universe. They discovered quasars, mysterious objects that appeared star-like but emitted as much energy as entire galaxies, later understood to be supermassive black holes actively consuming matter. They mapped the large-scale structure of the universe, finding that galaxies were not randomly distributed but clustered together in groups and superclusters, separated by vast voids. They measured the expansion rate of the universe with increasing precision, working backward toward the moment of creation. But for all its power, the 200-inch telescope represented a kind of endpoint for ground-based optical astronomy as it had been practiced. Making mirrors significantly larger than 200 inches seemed impractical with existing technology. They would be too heavy, too expensive, too difficult to support and control. And there was another fundamental problem that no amount of engineering could solve: the Earth's atmosphere. Even on the clearest nights at the best sites, air turbulence blurred stellar images, causing them to twinkle and dance. This atmospheric seeing limited the resolution of even the largest telescopes. They could gather more light than smaller instruments, revealing fainter objects, but they couldn't see finer details. The solution to the atmosphere problem came from an unexpected direction. During World War II, engineers had developed technologies for image enhancement and radio detection. In the post-war years, these technologies found new applications in astronomy. Radio astronomy emerged as a powerful new tool in the late 1940s and 1950s. Radio waves, with wavelengths millions of times longer than visible light, pass through clouds and atmospheric turbulence with minimal distortion. Radio telescopes, enormous dishes or arrays of antennas, could observe the universe in this invisible part of the electromagnetic spectrum, revealing phenomena that optical telescopes could never detect. In 1963, the Arecibo Observatory opened in Puerto Rico, featuring a 1,000-foot radio dish built into a natural sinkhole, the largest single-aperture telescope ever constructed at the time. Arecibo couldn't move or steer like conventional telescopes. Instead, it observed objects as the Earth's rotation carried them through its field of view. But its immense size made it exquisitely sensitive, capable of detecting incredibly faint radio signals from the cosmos. With Arecibo and other radio telescopes, astronomers discovered pulsars, rapidly spinning neutron stars emitting beams of radio waves like cosmic lighthouses. They mapped the spiral structure of our galaxy by detecting radio emission from hydrogen gas. They even began listening for signals from extraterrestrial civilizations. The realization that the universe emitted radiation across the entire electromagnetic spectrum, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, transformed astronomy in the second half of the 20th century. Each wavelength revealed different phenomena, different aspects of cosmic processes. Hot gas surrounding black holes emitted X-rays. Cool dust clouds glowed in infrared. Violent explosions produced gamma-ray bursts. To fully understand the universe, astronomers needed to observe it in all these wavelengths, but Earth's atmosphere blocked most of them. Only radio waves and visible light reached the ground with relative ease. The answer was obvious but challenging. Telescopes had to leave Earth entirely. They had to go into space, above the atmosphere, where they could observe the universe without interference, in wavelengths that never reached the ground. The space age, beginning with Sputnik in 1957, made this possible. Rockets could now carry scientific instruments beyond the atmosphere, at least briefly. The question was whether they could carry something as delicate and complex as a telescope and keep it functioning in the harsh environment of space. The first astronomical satellites were modest affairs. Small instruments carried aloft on rockets for brief flights above the atmosphere, gathering data for minutes before falling back to Earth. But these early experiments proved the concept. In 1962, the first X-ray astronomy satellite, called Uhuru, was launched from a platform off the coast of Kenya. Named with the Swahili word for freedom and launched on Kenya's Independence Day, Uhuru spent 2.5 years mapping the X-ray sky, discovering over 300 sources including X-ray binary systems where matter torn from normal stars spiraled into neutron stars or black holes, heating to millions of degrees and emitting intense X-rays in the process. The success of Uhuru and other early space observatories demonstrated that space-based astronomy was not just feasible but revolutionary. Throughout the 1970s and 1980s, NASA and other space agencies launched a series of increasingly sophisticated observatories. The International Ultraviolet Explorer, launched in 1978, operated for an astonishing 18 years, far exceeding its design life, and made over 104,000 observations of stars, galaxies, and solar system objects in ultraviolet wavelengths invisible from Earth's surface. Each mission revealed aspects of the universe that had been literally invisible before, hidden behind our protective but obscuring atmosphere. But the dream was always a large optical telescope in space, an instrument that could observe invisible light like the great ground-based telescopes, but without the blurring effects of atmospheric turbulence, achieving the theoretical resolution that the size of its mirror should allow. This dream began to take concrete form in the 1970s when NASA started planning what would become the Hubble Space Telescope. Named after Edwin Hubble, whose discoveries had transformed our understanding of the cosmos, this would be the most ambitious and expensive scientific instrument ever placed in orbit. The Hubble Space Telescope's primary mirror measured 94.5 inches, not nearly as large as the great ground-based reflectors, but it didn't need to be. Without atmospheric interference, Hubble could achieve resolutions 10 times better than ground-based telescopes of any size. The mirror was ground and polished to extraordinary precision, accurate to within a few millionths of an inch. The entire telescope weighed over 24,000 pounds and measured 43 feet long. It was designed to be serviced by astronauts in orbit, with instruments that could be replaced or upgraded as technology advanced, a capability that would prove crucial to the telescope's success and longevity. Hubble was launched aboard the Space Shuttle Discovery on April 24, 1990, amid enormous anticipation. Finally, humanity would see the universe with unprecedented clarity. But within weeks of the telescope's activation, scientists realized something was terribly wrong. The images were blurry, no better than ground-based telescopes could achieve. After extensive analysis, the problem was identified. The primary mirror had been ground to the wrong shape, off by about 2 microns at the edge, roughly 1/50th the width of a human hair. It was a catastrophic error, the result of a flaw in the testing equipment used during the mirror's fabrication. The most expensive scientific instrument ever built was, essentially, nearsighted. The error was a public relations disaster, but NASA engineers devised an ingenious solution. In December 1993, astronauts aboard the Space Shuttle Endeavour rendezvoused with Hubble and installed corrective optics, essentially prescription glasses for the telescope. The corrective optics Space Telescope Axial Replacement, or COSTAR, used small mirrors to compensate for the primary mirror's aberration. When new images came down after the repair mission, they were everything that had been promised: sharp, detailed, breathtaking. Hubble had been saved, and it would go on to become perhaps the most scientifically productive telescope in history. Over the next 3 decades, Hubble transformed our understanding of the universe in ways both profound and unexpected. It measured the expansion rate of the universe with unprecedented precision, helping determine that the universe is approximately 13.8 billion years old. It discovered that the expansion is actually accelerating, driven by a mysterious dark energy that makes up about 68% of the universe's total energy content. A discovery that earned the Nobel Prize in 2011, though Hubble's observations were crucial to confirming it. The telescope captured the deepest images ever taken of the cosmos, the Hubble Deep Field and its successors, showing that the universe contains hundreds of billions of galaxies, each with hundreds of billions of stars. Hubble also revolutionized the study of exoplanets, planets orbiting other stars. While it didn't directly image many exoplanets, they're too faint and too close to their parent stars. Hubble could analyze the light from distant stars as planets passed in front of them, detecting the chemical signatures of planetary atmospheres. It found evidence of water vapor, methane, and other molecules on worlds dozens or hundreds of light-years away, taking the first tentative steps toward characterizing the atmospheres of alien worlds and searching for potential biosignatures, chemicals that might indicate life. The stunning images Hubble produced became cultural icons, reproduced in textbooks, documentaries, and art galleries worldwide. The pillars of creation in the Eagle Nebula, towering columns of gas and dust where new stars are being born. The ethereal beauty of planetary nebulae like the helix, shells of gas expelled by dying stars. Colliding galaxies locked in gravitational embrace, their spiral arms distorted and streaming with newly formed stars. These images did more than advance scientific knowledge. They changed how humanity visualized and related to the cosmos, making the universe's grandeur and beauty accessible to everyone. Even as Hubble orbited Earth, ground-based telescope technology was undergoing its own revolution. In the 1980s and 1990s, astronomers developed adaptive optics systems that could partially compensate for atmospheric turbulence in real time. These systems used deformable mirrors that changed shape hundreds of times per second, correcting for the distortions caused by air currents. By measuring how a bright star or artificial laser guide star is distorted by the atmosphere, computers can calculate the corrections needed and adjust the mirror accordingly. The result: ground-based telescopes could now approach the theoretical resolution limits of their apertures, at least for bright objects. This breakthrough enabled the construction of a new generation of extremely large ground-based telescopes. The twin Keck telescopes in Hawaii, completed in 1993 and 1996, featured 33-foot mirrors, far larger than anything previously built. But these weren't single pieces of glass. Each Keck mirror consisted of 36 hexagonal segments, each individually controlled to maintain the correct overall shape. This segmented mirror design solved the problem that had limited telescope size for decades. You could build mirrors as large as you wanted by assembling them from smaller pieces. The Keck telescopes, equipped with adaptive optics and sitting atop Mauna Kea at nearly 14,000 feet above sea level, could achieve resolutions rivaling Hubble's in infrared wavelengths. The success of segmented mirrors opened the door to truly enormous ground-based telescopes. Projects like the Very Large Telescope in Chile, the Gemini Observatory with twin 26.5-foot telescopes in Hawaii and Chile, and eventually the planned 30-meter telescope and European Extremely Large Telescope with mirrors measuring, as their names suggest, 30 and 39 meters respectively. These giants would dwarf even Keck, gathering enough light to study individual stars in distant galaxies, to characterize the atmospheres of Earth-like exoplanets, to probe the epoch when the first stars formed in the infant universe. As the 21st century began, astronomers dreamed of pushing beyond even Hubble's capabilities. The telescope had performed magnificently, far exceeding its design life, but it observed primarily in visible and near-ultraviolet wavelengths. To peer deeper into cosmic history, to see the very first galaxies forming in the infant universe, required observing in infrared wavelengths, the stretched, redshifted light from the most distant objects, light that had been traveling toward us for over 13 billion years. This required a new kind of space telescope, one optimized for infrared observation, cooled to extraordinarily low temperatures to prevent its own heat from overwhelming the faint signals it sought to detect. The James Webb Space Telescope, conceived in the late 1990s as Hubble's successor, would be that instrument. Its primary mirror would measure 21.3 feet across, nearly 3 times Hubble's diameter and thus about 6 times the light-gathering area. But launching something that large presented an impossible challenge. No rocket fairing was big enough. The solution was elegant and terrifying. The mirror would be segmented like Keck's, but the segments would fold up for launch and unfold in space. 18 hexagonal beryllium segments, each coated with a microscopically thin layer of gold to enhance infrared reflection, would deploy and align with nanometer precision to form a single, perfect optical surface. Everything about Webb was unprecedented. Unlike Hubble, which orbits just a few hundred miles above Earth, Webb would be positioned at the second Lagrange point, L2, nearly 1 million miles away, where the gravitational effects of Earth and Sun balance to create a stable location. At L2, Webb could keep its back permanently to the Sun, Earth, and Moon, allowing its 5-layer sunshield, as large as a tennis court, to protect the telescope and cool it to -370 degrees Fahrenheit. Cold enough that its own infrared glow wouldn't overwhelm the faint signals from distant galaxies. The technical challenges were staggering. The development took decades longer than planned, and the cost ballooned to nearly $10 billion. But on Christmas Day 2021, the James Webb Space Telescope finally launched aboard an Ariane 5 rocket from French Guiana. For the next month, as the telescope traveled to L2, it executed the most complex series of deployments ever attempted in space, unfolding its sunshield, extending its secondary mirror support structure, and finally unfurling its primary mirror segments. Every step had to work perfectly. There would be no repair mission like the one that saved Hubble. Webb was too far away for astronauts to reach. The deployment succeeded flawlessly, and in July 2022, the first images from Webb were released to the public. The clarity and depth were stunning. Galaxies that appeared as faint smudges in Hubble images resolved into elegant spirals with Webb, their structures visible in unprecedented detail. Webb's infrared vision allowed it to peer through dust clouds that block visible light, revealing stellar nurseries where new stars are being born. It captured images of galaxies as they appeared just a few 100 million years after the Big Bang, some of the earliest structures in cosmic history. Their light stretched into the infrared by the universe's expansion over more than 13 billion years. Webb's observations quickly challenged and refined our understanding of galaxy formation. The early universe, it turned out, was more structured and complex than theoretical models had predicted. Galaxies formed earlier and grew larger faster than expected. Some of the distant objects Webb detected appeared surprisingly mature for their age, suggesting that the process of galaxy assembly in the early universe was more efficient or occurred through different mechanisms than previously thought. Each observation raised new questions even as it answered old ones, a hallmark of truly transformative scientific instruments. Beyond distant galaxies, Webb revolutionized the study of exoplanets. Its infrared sensitivity and spectroscopic capabilities allowed it to analyze the atmospheres of planets orbiting other stars with unprecedented precision. In 2022, Webb detected clear signatures of water vapor, carbon dioxide, and other molecules in the atmosphere of WASP 96b, a hot Jupiter-like planet hundreds of light-years away. For smaller, rocky exoplanets more similar to Earth, Webb could search for biosignatures, combinations of gases like oxygen and methane that on Earth are primarily produced by life. The telescope couldn't definitively prove the existence of alien life, but it could identify promising candidates for more detailed study. While space telescopes captured the public imagination, ground-based astronomy continued to evolve and thrive. The next generation of extremely large telescopes was moving from planning to construction. The giant Magellan telescope, under construction in Chile, would use 7 27-foot mirrors working together to create the equivalent of an 80-foot telescope. The 30-meter telescope, planned for either Hawaii or the Canary Islands depending on unresolved political and cultural considerations, would feature a segmented mirror 98 feet across, gathering 9 times more light than the largest current telescopes and achieving resolutions 13 times better than Hubble in infrared wavelengths. The European Extremely Large Telescope, also under construction in Chile's Atacama Desert, would be the largest optical telescope ever built, a 128-foot, segmented primary mirror composed of 798 individual segments, each requiring constant adjustment to maintain the correct overall shape. This behemoth would gather 15 times more light than the largest current telescopes, allowing it to study Earth-like exoplanets, to observe the very first stars and galaxies, and perhaps to detect the subtle spectral signatures that might indicate biological processes on distant worlds. Its adaptive optics system would use multiple laser guide stars and deformable mirrors to achieve resolutions approaching the theoretical diffraction limit. These extremely large telescopes represented a philosophical commitment to ground-based astronomy despite the obvious advantages of space. They were cheaper to build and operate than space telescopes, easier to upgrade and repair, and could incorporate cutting-edge technologies as they became available. Their enormous light-gathering power meant they could study objects too faint even for Webb to detect. And there was something profound about maintaining a direct, physical connection to the cosmos, observing light that had traveled across space and time, arriving finally at a human-made mirror on a mountaintop, funneled to instruments built by human hands, interpreted by human minds. But the future held more than just larger mirrors. Radio astronomy was undergoing its own revolution with interferometry, combining signals from multiple radio telescopes separated by thousands of miles to create the equivalent of a single telescope as large as the Earth itself. The Event Horizon Telescope, a global network of radio dishes, used this technique to capture the first direct image of a black hole in 2019, showing the shadow cast by the supermassive black hole at the center of the galaxy M87 against its glowing accretion disk. That image, a bright ring of light surrounding a dark circle, was the first direct visual evidence of black holes, objects so extreme that they warp space and time itself. The square-kilometer array, under construction in Australia and South Africa, would eventually comprise thousands of radio antennas spread across 2 continents, with a total collecting area of 1 square kilometer, hence its name. This massive instrument would be 50 times more sensitive than any existing radio telescope, capable of detecting incredibly faint signals from the distant universe. It would map the distribution of hydrogen gas throughout cosmic history, trace the large-scale structure of the universe, and potentially detect radio signals from technological civilizations around other stars, if such civilizations exist and are broadcasting. As these projects advanced, astronomers were also developing entirely new types of observatories. Gravitational wave detectors like LIGO, the Laser Interferometer Gravitational Wave Observatory, used lasers and mirrors to detect the infinitesimal ripples in spacetime caused by colliding black holes and neutron stars. While not telescopes in the traditional sense, they opened a completely new window on the universe, allowing astronomers to hear cosmic events through gravity itself rather than through light. The first detection in 2015, confirming Einstein's century-old prediction of gravitational waves, earned the Nobel Prize and inaugurated the era of multi-messenger astronomy. Studying cosmic phenomena through multiple channels simultaneously, the evolution of the telescope has always been driven by a simple desire: to see farther, to see more clearly, to understand what lies beyond the limits of human vision. But as we move deeper into the 21st century, telescopes are revealing not just what the universe looks like, but what it's made of, how it began, and perhaps even how it will end. The telescope has become more than an optical instrument. It has become humanity's most powerful tool for asking fundamental questions about existence itself. One of the most profound mysteries these modern instruments are helping to unravel is the nature of dark matter. Throughout the 20th century, astronomers accumulated evidence that the visible matter in the universe, stars, gas, dust, everything we can see, accounts for only about 15% of the total matter. The rest, dubbed dark matter, reveals itself only through its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain far more mass than their visible components suggest. Gravitational lensing, the bending of light by massive objects, shows concentrations of matter where nothing visible exists. Modern telescopes are mapping this invisible cosmic scaffolding with increasing precision. The Dark Energy Survey, using the Blanco 4-meter telescope in Chile, catalogued hundreds of millions of galaxies between 2013 and 2019, mapping how dark matter is distributed across billions of light-years. By measuring how the light from distant galaxies is distorted by intervening dark matter, a phenomenon called weak gravitational lensing, astronomers can create three-dimensional maps of dark matter distribution. These maps reveal that dark matter forms a cosmic web, with galaxies forming along dense filaments while vast voids contain almost nothing. The Vera C. Rubin Observatory, which began operations in Chile in 2023, takes this mapping to unprecedented scales. Named after the astronomer who provided crucial evidence for dark matter's existence, the Rubin Observatory features a 27.5-foot primary mirror and the largest digital camera ever built for astronomy, a 3.2 gigapixel instrument weighing 3 tons. Every 3 nights, this observatory surveys the entire visible sky, capturing images of billions of galaxies and tracking how they change over time. The Legacy Survey of Space and Time, or LSST, will generate more astronomical data in its first week than all previous telescopes combined have collected throughout history. This flood of data is transforming astronomy from an observational science into something more akin to big data analytics. Machine learning algorithms sift through millions of images, identifying interesting objects, supernovae, asteroids, variable stars, that would take human astronomers lifetimes to find manually. Artificial intelligence helps classify galaxies, detect subtle patterns, and even discover entirely new types of astronomical objects. The telescope itself becomes just one component in a vast system that includes not just optics and detectors, but massive data storage, high-speed networks, and sophisticated software that in some ways sees things human astronomers might never notice. Meanwhile, the search for life beyond Earth has become one of the primary drivers of telescope development. The discovery of thousands of exoplanets, planets orbiting other stars, has transformed this search from speculation to observational science. The first confirmed exoplanet orbiting a Sun-like star was discovered in 1995 by Swiss astronomers Michel Mayer and Didier Queloz using the radial velocity method, detecting the tiny wobble a planet's gravity induces in its parent star. That discovery, which earned the 2019 Nobel Prize in Physics, opened the floodgates. We now know of over 5,000 confirmed exoplanets, with thousands more candidates awaiting verification. NASA's Kepler Space Telescope, which operated from 2009 to 2018, revolutionized exoplanet discovery by staring continuously at a single patch of sky containing about 150,000 stars, watching for the tiny dip in brightness that occurs when a planet passes in front of its star. Kepler discovered over 2,700 confirmed exoplanets and revealed that planets are extraordinarily common. Current estimates suggest there are more planets than stars in our galaxy, and potentially billions of Earth-sized worlds in habitable zones where liquid water could exist on their surfaces. The Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, continues this work, surveying the entire sky and focusing on the nearest, brightest stars where follow-up observations are easiest. But finding potentially habitable worlds is only the first step. Understanding whether they actually harbor life requires analyzing their atmospheres, searching for biosignatures, gases or combinations of gases that on Earth are primarily produced by biological processes. This is where the James Webb Space Telescope and the upcoming generation of extremely large ground-based telescopes become crucial. In 2024, Webb detected potential biosignature gases in the atmosphere of K2-18b, a sub-Neptune planet about 120 light-years away in the habitable zone of its star. The detection of dimethyl sulfide, a gas on Earth produced only by marine phytoplankton, alongside carbon dioxide and methane, sparked intense scientific debate. Was this evidence of life? Or could these gases be produced through non-biological chemistry we don't yet fully understand? The upcoming Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will add another powerful tool to the search. Named after NASA's first chief of astronomy who championed the Hubble project, Roman features a 7.9-foot mirror, similar in size to Hubble's, but with a field of view 100 times larger. While Webb peers deeply at small patches of sky, Roman will conduct vast surveys, discovering thousands of new exoplanets through gravitational microlensing, a technique that detects planets by the brief brightening they cause when passing in front of distant stars. Roman will find planets that other methods miss, including free-floating worlds that were ejected from their star systems, drifting alone through interstellar space. Each of these instruments, from radio dishes to infrared space telescopes to gravitational wave detectors, is part of an increasingly interconnected web of observation. When a gravitational wave detector registers the collision of two neutron stars, optical and radio telescopes around the world immediately slew to that position in the sky, capturing the light from the explosion, a kilonova, that produces heavy elements like gold and platinum. When a gamma-ray burst is detected by satellites, ground-based telescopes quickly observe the fading afterglow, measuring its distance and properties. This coordinated, multi-wavelength approach, observing cosmic events simultaneously across the entire electromagnetic spectrum and beyond, reveals aspects of these phenomena that no single telescope could capture alone. The next frontier extends even beyond traditional telescopes. China's 500-meter aperture spherical telescope, or FAST, the world's largest filled-aperture radio telescope since Arequipa's collapse in 2020, is searching for pulsars and conducting SETI, the search for extraterrestrial intelligence, observations. NASA is planning missions to place telescopes on the far side of the Moon, where they would be shielded from Earth's radio interference and could detect ultra-low-frequency radio waves that never penetrate our ionosphere. Concepts exist for space-based interferometers with telescopes separated by millions of miles, achieving resolutions that could directly image continents on exoplanets dozens of light-years away. Perhaps most audaciously, some astronomers are exploring the possibility of using gravitational lensing itself as a telescope. Einstein's equations predict that the sun's gravity bends light passing near it, focusing that light at a point about 550 astronomical units away, roughly 14 times farther than Pluto. A spacecraft positioned at this distance could, in theory, use the sun as a gravitational lens to magnify distant objects by factors of billions, potentially resolving details on exoplanets that would otherwise be impossible to see. Such a mission would take decades just to reach the focal point, but it represents the kind of ambitious thinking that has always driven telescope development, finding new ways to see what was previously unseeable. As we look toward the future of the telescope, we find ourselves at a remarkable juncture, standing between what has been achieved and what might yet be possible. The instruments we've built have already answered questions that previous generations could barely articulate, yet each answer seems to open doors to deeper mysteries, stranger possibilities, realms of cosmic understanding that remain tantalizingly just beyond our current reach. One of the most ambitious projects on the horizon is the Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s. Unlike the ground-based LIGO detectors that discovered gravitational waves from colliding stellar mass black holes, LISA will operate in space, using 3 spacecraft flying in formation 1.6 million miles apart, forming a giant triangle. This enormous baseline will allow LISA to detect gravitational waves at much lower frequencies, the ripples in spacetime produced by supermassive black holes merging at the centers of galaxies, events so energetic they shake the very fabric of the universe. LISA will essentially allow us to hear the universe's deepest bass notes, gravitational symphonies that have been playing since the first massive structures formed in the cosmos. The quest to observe the epoch of the first stars, the so-called cosmic dawn, occurring between 100 and 400 million years after the Big Bang, is driving development of instruments specifically designed for this purpose. While James Webb can glimpse some of the earliest galaxies, seeing individual first-generation stars requires even more sensitivity and resolution. Concepts like the Habitable Exoplanet Observatory, or HABEX, and the Large UV Optical IR Surveyor, or LUVOIR, envision space telescopes with mirrors ranging from 13 to 50 feet in diameter, equipped with coronagraphs and starshades, enormous flower-shaped screens flying thousands of miles in front of the telescope to block starlight and reveal planets that would otherwise be lost in their star's glare. The starshade concept itself represents an elegant solution to one of astronomy's hardest problems. A planet like Earth orbiting a sun-like star appears about 10 billion times fainter than its star. Imagine trying to see a firefly next to a searchlight from across the country. No amount of optical precision can completely eliminate the starlight bleeding into the telescope. But a starshade, a precisely shaped screen positioned perfectly between the telescope and the target star, can block the starlight before it even reaches the telescope's optics. NASA has been testing prototypes and refining the concept, working toward a mission that could launch in the 2030s or 2040s and directly image Earth-like worlds around nearby stars, potentially detecting the blue of water oceans, the green of vegetation, the telltale signs of a living world. Ground-based telescope technology continues to push boundaries in unexpected ways. The Cherenkov Telescope Array, under construction at sites in Chile and Spain, will consist of over 60 telescopes working together to detect very high-energy gamma rays, the most energetic form of light in the universe. These gamma rays don't reach Earth's surface. Instead, when they strike the upper atmosphere, They create cascades of particles that emit brief flashes of blue Cherenkov light. The array of telescopes captures these flashes, and computers reconstruct the original gamma rays' energy and direction. This technique allows astronomers to study some of the universe's most violent phenomena: supermassive black holes actively consuming matter, the remnants of supernova explosions, and perhaps even signatures of dark matter particles annihilating each other. The idea of neutrino telescopes has transformed from theoretical curiosity to operational reality. Neutrinos are ghost-like particles that barely interact with matter. Trillions pass through your body every second, passing through Earth as if it weren't there. But very rarely, a neutrino collides with an atom, and this collision can be detected. The IceCube Neutrino Observatory, completed in 2010, consists of 5,160 optical sensors embedded deep in a cubic kilometer of ice at the South Pole. When a high-energy neutrino strikes an atom in the ice, it produces a charged particle that creates a cone of blue light, Cherenkov radiation again, that the sensors detect. IceCube has detected neutrinos from supernovae, from the Sun, and in 2018, traced a high-energy neutrino back to a blazar, a supermassive black hole with its jet pointed directly at Earth, 4 billion light-years away, opening yet another window on the cosmos. The square-kilometer array, when completed in the late 2020s, will revolutionize our understanding of cosmic magnetism and the structure of the universe at the largest scales. One of its key science goals is to map the distribution of neutral hydrogen throughout cosmic history by detecting the 21-centimeter line emission, a specific radio wavelength that hydrogen naturally emits. By observing how this hydrogen is distributed across billions of years of cosmic time, astronomers can trace how the large-scale structure of the universe evolved, how galaxies formed and clustered, and potentially test fundamental theories about the nature of gravity and dark energy. The array's sensitivity will be so extraordinary that it could detect an airport radar on a planet orbiting a star dozens of light-years away, though actually finding such signals, if they exist, would require searching vast numbers of stars with enormous patience. Another transformative development is the rise of ultraviolet and X-ray imaging beyond what Hubble and current X-ray satellites can achieve. The proposed Lynx X-ray Observatory, if funded, would be 50 times more sensitive than any existing X-ray telescope, capable of detecting individual X-ray photons from the supermassive black holes that powered the first quasars in the infant universe. Lynx could trace the flow of hot gas between galaxies, map the distribution of heavy elements produced in the first generations of stars, and study the processes by which black holes grow from stellar remnants to the billion solar mass monsters found at the centers of galaxies. Understanding how these first black holes formed so quickly remains one of the great puzzles in astrophysics, and only more powerful X-ray telescopes can provide the observational evidence needed to solve it as these instruments grow more sophisticated. Astronomers are also returning to an old idea with new technology: interferometry with optical telescopes. While radio astronomers have used interferometry for decades, combining light from separate optical telescopes is far more challenging. The wavelengths are thousands of times shorter, requiring positioning and timing precision measured in nanometers and femtoseconds. But the rewards are extraordinary. The Very Large Telescope Interferometer in Chile can combine light from 4 27-foot telescopes and several smaller auxiliary telescopes, achieving resolutions equivalent to a single telescope 426 feet across. This has allowed astronomers to directly measure the diameters of stars dozens or hundreds of light-years away, to observe material swirling around black holes, and even to image the surfaces of nearby giant stars, revealing spots and features on stellar surfaces. The ultimate expression of this technology might be space-based optical interferometry. Concepts like the Space Interferometry Mission, repeatedly proposed and deferred due to cost and technical challenges, envision multiple telescopes flying in precise formation in space, combining their light to achieve resolutions that could not only image continents on exoplanets but could potentially detect the gravitational wobble caused by Earth-mass planets around hundreds of nearby stars. Such precision would also enable tests of general relativity in the strong field regime around black holes, measurements of cosmological parameters with unprecedented accuracy, and perhaps discoveries we cannot yet anticipate. All these developments, from gravitational wave detectors to neutrino observatories to ever larger optical telescopes, reflect a fundamental shift in how we observe the universe. Astronomy is no longer confined to collecting photons of light, though that remains central. We now observe through gravitational waves, neutrinos, cosmic rays, every possible messenger that carries information across cosmic distances. We observe across the entire electromagnetic spectrum simultaneously, from ultra-low frequency radio waves to the highest energy gamma rays. We combine data from dozens of instruments, each contributing pieces to a more complete picture. This multi-messenger approach recently demonstrated its power when, in 2017, gravitational wave detectors registered the merger of two neutron stars. Within seconds, an automatic alert went to observatories worldwide. Gamma-ray satellites detected a burst from the same direction. Optical telescopes caught the fading light of the kilonova. The explosion produced when neutron-rich material ejected by the collision undergoes rapid nuclear reactions. X-ray and radio telescopes tracked the aftermath for weeks. Spectroscopy revealed the signatures of newly synthesized heavy elements, confirming that neutron star mergers are cosmic forges that produce much of the gold, platinum, and other precious metals in the universe. No single telescope could have told this complete story, and so we return, our celestial voyage complete. The telescope began as a question, held in human hands. It has become a quiet witness, orbiting in perpetual night, gathering whispers from the dawn of time. We are the bridge between the first curious glance and the infinite gaze, between the glass lens and the living eye, between the distant light and the quiet wonder it stirs within you tonight. Hold that wonder as you drift, for in your dreams, you need no instrument. Your mind is the ultimate observatory, mapping constellations of memory and myth. The stars are not distant now. They are with you. In the gentle dark, you are home.